Hello, chemistry students. Professor Sean McMahon here, and in this lecture, we're going to continue our discussion of Chapter 6 and compounds. And we are going to focus right now on drawing what are referred to as structural formulas or Lewis dot structures for covalent molecular compounds. So where we left off last time was we were discussing how with the Lewis dot symbols that we learned in Chapter 4 with atomic structure, that the dots represent the number of valence electrons for that element. We can see here that hydrogen has one dot because it has one valence electron. The oxygen has 6. They need a total of 8 to have an octet to be stable, like neon. To do that, they're willing to share their unpaired electrons with each of the hydrogen's unpaired single electrons to form bonds. Again, when we show where there's an overlap, bonds are actually drawn as lines, so those represent shared pairs. Unshared pairs are referred to as lone pairs, and we actually use the dots to represent those. But we can also see that the oxygen has its octet because it has 1, 2 in this lone pair, 3, 4 in this lone pair. Then the bonds each have 2 electrons, 5, 6, 7, 8. It has an octet and it's stable. The hydrogen has its duet, so it's stable because it has an electron configuration of 1s2 like helium, the noble gas, and having its principal energy level 1 filled. We saw the same thing with nitrogen. Nitrogen has 5 valence electrons. It needs 3 more electrons to be like an octet, so it's willing to share with 3 hydrogens, its unpaired electrons, and form 3 single bonds in this case and 1 lone pair. We have carbon, and it has 4 unpaired electrons, so it likes to form 4 bonds. Now, one of the things I want to mention is here we see that oxygen likes to have 2 bonds and 2 lone pairs, but those 2 bonds could be what's referred to as a double bond and 2 lone pairs. So that is a possibility. So we see that with structures like CO2. The nitrogen has, in this case, we see 3 single bonds and 1 lone pair, or it could have a double and a single and a lone pair, or a triple because it still adds up to 3 bonds, 1 lone pair. So we see the double and the triple as an example in this particular structure. And we see a triple in this particular structure. So we can see that as long as the total is that many bonds, it's still a stable Lewis dot structure. With carbon, we see here that it has 4 single bonds. Up here, we see an example where I could have 2 doubles. With the acetylene example, I could see where I have a triple and a single. That was the acetylene, right? Or I could have a double and 2 singles. Like in this case here with ethane or ethylene. So why is that important? These bonding patterns will help us understand when we do Lewis dot structures. It'll also help us see that if we need a single, double, or triple bond. So basically each bond has 2 electrons, okay? So in a single bond, you have 2 atoms that share 1 pair of valence electrons. The example, hydrogen. Each of these hydrogens have 1 single electron as they approach, and there's an overlap in their orbitals. Now the 2 electrons are between them, so they're sharing that those 2 electrons that make them stable, and we draw it as a single bond. With double bonds, you typically have 2 pairs of valence electrons being shared. So in this case, this is actually omitting the lone pairs, but in this example of oxygen, we have a double bond, and then we have 2 lone pairs for each of these, and what we're actually seeing is both have an octet, 2, 4, and then this bond 6, 8. Same thing here, 2, 4, 6, 8. Triple bonds are where you have 3 pairs of valence electrons being shared, like in this example of nitrogen that I said earlier. So I have 3 bonds and the 3 are being shared. We see the 3 odd electrons all come together to form 3 bonds, and it's basically a triple bond. So there are steps when it gets a little more complicated, and I would always recommend following these steps. So the first step is you always got to determine the total number of valence electrons. And that's why your periodic table is the best cheat sheet, because again, your group number, and remember, I use the old school, the A portions for the representative elements. Your group number is going to tell you how many valence electron. So nitrogen is group 5A, which results in 5 valence electrons, and we can write out 5. Fluorine is group 7A, so each fluorine has 7, and there's 3 of them, so 7 times 3 is 21. So my total valence electrons is 26 valence electrons for this species. Now I say species because we could draw Lewis dot structures for ions, polyatomic ions, and molecules, and atoms actually as well. So the reason why I say species is we can use Lewis dot structures for all of this. Now, this particular species is, if you had to guess, a binary covalent compound. Now, why is it a binary covalent compound? Well, it's covalent because it's only nonmetal with nonmetal, nitrogen and fluorine. It's binary because there's only 2 types of atoms, nitrogens and fluorines. It's a compound because it's neutral. So it's a binary covalent compound because it's 2 types of atoms. It's covalent because they're both nonmetal, and it's a compound because it's neutral. Okay. So now we want to arrange it where we write the elemental symbols in the correct locations to represent the structure of this really molecule. This, and by the way, everyone should know the name of this. This is nitrogen trifluoride. And again, let's emphasize that we need to use the prefixes because this is covalent, binary covalent. And for the first element, nitrogen, we do not need to go mono. So it's nitrogen trifluoride. So when we're sketching the symbols together, okay, we need to determine which one's the central atom. Typically, the central atom is the most metallic. So nitrogen is further away from fluorine, so that's going to be in the center. And we are going to surround it with the fluorines as what are called exterior atoms, or atoms in the peripheral. So the central atom only appears once in the formula. That's not always the case, okay? But in this case, it's true. Typically, the central atom is the most metallic. If you have a compound that has hydrogen, oxygen, and an additional element, so this is where you have more than just binary, right? You're going to have the non-metal be the central atom. So for an example, in nitric acid, it would be nitrogen. And sulfuric acid, it would be sulfur, okay? But let's go back to what we're doing here. Carbon is typically the central atom in pretty much all carbon-containing compounds. In fact, when we have more than one central atom, you typically want to link all the carbons first. It's called a carbon skeleton. For this class, we're primarily focusing on simple, single central atom species. We'll see in lab, we will expand that to some of the organic examples. If I have hydrogen and fluorine, those are always exterior atoms, okay? Why? They like to form one bond. Hydrogen never exceeds a duet, right? Because it's in the first energy level. So it has one lone valence electron, and it will form one bond, typically with something like another hydrogen. Fluorine, it's group 7A, and it needs one more electron, so it tends to form a bond as well. And another example could be hydrogen, for example. But it's typically not a central atom because it's not very metallic, okay? So that's another reason why that tends not to be a single or a central atom. But these 2 elements tend to form only single bonds. So we're going to have nitrogen as our central atom, and that's again because it's furthest away from the upper right-hand corner. And now I need to draw single bonds to make this species connected and traveling as a group. And those single bonds, those lines, are representing two shared electrons. Okay, so we actually draw the lines. And now what I need to do is for every bond, I need to subtract 2 electrons. So there's 3 bonds, 2 times 3 electrons. I've used 6, I have 20 electrons remaining. So what do I do with the 20 remaining electrons? The first thing I need to do is I need to attach them to the outer atoms. So the fluorines, sometimes referred to as the peripheral atoms, to satisfy their octets. So each fluorine right now has 2 electrons. Okay, so because in that bond, they're sharing the 2 electrons with nitrogen, it still has 2 electrons around it. So each of these fluorines needs only 6 more electrons to get 8. So to get the octet for the fluorine, I'm going to place lone pairs around the outer atoms until they satisfy their octets. So 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used 18 electrons to satisfy the octets for the outer atoms, and in this case, fluorine. So I need to subtract those 18. What that does is it leaves remaining 2 electrons. So what do I do with these 2 remaining electrons? Well, so I'm kind of reminding you, hydrogen can only have 2 electrons, so you can't have any lone pairs. Okay, so if there's any peripheral atoms and they're hydrogens, do not put lone pairs on them. That's typically for peripheral or outer atoms. When you're satisfying the octets, it's not going to be hydrogen because it wants a duet. Because we have 2 remaining electrons and we need to do something with these 2, we are going to figure out where should they go. They're going to go on the central atom. They're going to go on the central atom because if we see with the 3 bonds, the nitrogen only had 6 valence electrons around it. By adding these 2 remaining atoms as a lone pair, an unshared pair, we actually now have no more from the total, and the nitrogen satisfies its octet. We also see that the nitrogen follows the bonding pattern that we talked about earlier, where it has 5 valence electrons, and the 3 of the 5 that are unpaired are used to form bonds. Now, it could be a triple, it could be a double and a single, or it could be 3 singles in the case of nitrogen trifluoride. So that's an example of this particular one. Now, sometimes the central atom will not have an octet. That's when we'll have to remove lone pairs from exterior atoms to satisfy octets. Okay, so what I'll do is I'll kind of do that in the example exercises and walk you through that. The one thing about Lewis dot structures is we have to realize Lewis dot structures, essentially with Lewis dot structures, they're with Lewis dot structures, they are only 2D. So they're somewhat limited. They cannot show the full display of the bonds for particular molecules. So what do I mean by that? Well, I mean that in some cases, I could actually draw the same molecule 2 different ways. Okay, so what do I mean? So for SO2, now I kind of jumped straight to the Lewis dot structure. So I'd like to actually draw the Lewis dot structure for you guys. Yeah, I'd like to draw the Lewis dot structure for you. So let's first do that. If we have sulfur, the sulfur, I need to figure out first total valence electrons. It's group 6A. I have 6 valence electrons. I have oxygen. There's 2 oxygen. So I have 2 oxygen. Each of those, group 6A, have 6 valence electrons. So I have a total of 6 plus 12 equal 18 valence electrons. So that's my total for SO2. The next thing I need to do is I need to figure out, all right, which one of these is the central atom? Well, because sulfur is below oxygen, it's more metallic, it's the central atom. And then I know that, okay, I have oxygen as the outer atom or the peripheral. The next thing I do is I have to attach single bonds. So if I do that, 1, 2, because I have to have everything attached, I've used 2 bonds. Each bond has 2 electrons. I've used 4 electrons. So if I subtract 4 from this, I have 14 valence electrons to distribute still. So if I go to the next rule, it says add lone pairs to the outer atoms to satisfy octets. Each oxygen has 2 electrons. They need 6 more. So that would require 3 lone pairs. So 2, 4, 6, and then with the bond, that's 8. 2, 4, 6, 8, with the bond, that's 8. But I've actually, with the lone pairs that I've added, used 2, 4, 6, 8, 10, 12 of the 14. So I have to subtract that. Now, with the remaining 2, what should I do? Gonna attach it to the central atom, like it said. Now, remember that 5th rule? That 5th rule said, okay, if the central atom has an octet, you are done. If I look at sulfur, it does not have an octet. It has 6 electrons, 2 in this bond, another 2 in this bond, that makes 4 in a lone pair. That's only 6. So that last rule was I actually incorrectly chose to add lone pairs where there actually wasn't one. So I'm going to take this lone pair and I'm going to add it here. And what that will do is create this structure. So when I see that, what I notice now is the sulfur actually has an octet. It has 2 electrons in this first single bond, 4, 6, and then the lone pair makes a total of 8. It has an octet. It's happy. This oxygen has an octet because 2, 4, 6, 8. It's happy. This oxygen has an octet because 2, 4, 6, 8. It's happy. What that looks like, and I know this is probably hard to see, but it essentially looks like this structure right here. So what I'm showing you is the sulfur's in the center. This oxygen to my right has a double bond. The oxygen to my left has a single bond. And this on the top here represents that lone pair. So here's that lone pair. The problem with 2D is it's flat. And what we have to understand is I can take this electron, and it's in 2D, but I can rotate it 180 degrees. So what does that mean? Well, if I actually rotate this 180 degrees, I'm actually getting, right, because all I'm doing is rotating this 180 degrees, I'm getting this structure. So these are referred to resonance structures. So what do I mean? 2 or more Lewis structures for the same molecular polyatomic ion, but a different arrangement. The reason why this is different is because on 2D, it appears that the double bond is on the right in this structure, and in this structure, it appears on the left, where in actuality, it's the same molecule. It's just a rotation in 3D of 180. So with Lewis-Dot structures, when you see these 2 different forms of sulfur dioxide, because that's the name of this, sulfur dioxide, both of these are correct. But there's 2 resonance structures because there's 2 ways to draw this, okay? So now we're going to take everything we talked about and drawing the molecules, and we're going to apply it to these particular molecules. Now, some of you are really good. You could probably do this without following every step. I'm still going to do it. So I have hydrogen, and hydrogen each has, there's two of them, one valence electron. How do I know? Again, it's group 1A, okay? So hydrogen's group 1A on the periodic table. There's one sulfur plus, and each sulfur has six. So I have a total of 8 valence electrons. So that's the first step. I have 8 valence electrons. Second, who's the central atom? Hydrogen can never be the central atom, ever. Okay, so what are we going to do? Sulfur is going to be in the middle, and hydrogen's always an exterior atom. For this to be a compound, and again, I know this is a compound. Why? Well, there's no charge. So it's a compound. Is it ionic or covalent? It's covalent. Why is it covalent? Non-metal, non-metal. Can we be more specific? Yes, it's binary covalent. Can we be even more specific? Yes, it's a binary acid. How do I know it's an acid? It has hydrogen and a non-metal, and it's binary. Could I name this? Binary acids have the hydro prefix. This is hydrosulfuric acid. So we learned about this, but now we're going to draw the structure. So I have 8 valence electrons. The first thing I have to do is I have to draw the bonds. There's 2 bonds, 2 electrons per bond. I've used 4. So 8 minus 4 means I have 4 remaining. With the 4 remaining, I add lone pairs first to the outer atoms. But there is an exception. I do not add lone pairs to hydrogens. Hydrogens do not want octets. They only want duets. So each of these exterior hydrogens are already happy because they have their first energy level filled like helium. So what do I do with these remaining 4? I add them to the central atom to make an octet for the central. So sulfur has 2, 4, 6, 8, but I added 2 lone pairs. I added 4. I subtract 4. There's no more electrons to distribute. And when I look at this, this is stable. This is, right, hydrosulfuric acid, and the sulfur has basically an octet. Very similar to, what water would have, okay? Let's try this. So what type of compound is this? Binary covalent. Now, a lot of you might say, well, wait a second. Silicon is a metalloid. That is true. Silicon is a metalloid, and fluorine is a nonmetal. So it's not that this is nonmetal, but metalloids, remember, are unusual that they have both metal and nonmetal characteristics. When it comes to bonding, silicon does not produce a charge. It shares its electron. So this is still a covalent compound, okay? So following the rules of binary covalent, how would I name this? This is silicon tetrafluoride. So silicon tetrafluoride. So the first thing I need to do is figure out how many valence electrons. So silicon has 4, plus there's 4 fluorine. Each of those have 7. So 4 times 7, 28. 28 plus 4 is a total of 32 valence. I'll put it over here, 32 valence electrons. There's my total. Now, which one is going to be in the center? Remember, hydrogen, fluorine, never in the center, so we know it's silicon. And I have 4 fluorines. First rule, I have to connect everything. 4 bonds, each bond has 2 electrons, 4 times 2. So 4 times the -2 gives me, subtract 8, I have 24 remaining electrons. Next rule, I have to satisfy the octets to the outer atoms. So fluorine, I need to add 3 lone pairs to each of them so that they have an octet. So when I do that, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up, I have no more electrons, but everything's happy and has an octet. Why does silicon have an octet? It has 4 bonds, 2 electrons in each bond, that's 8. Why is fluorine happy? It has 3 lone pairs, which is the 6, and then 1 bond. Again, this goes back to the bonding patterns. Remember, fluorine is group 7A. It has 7 valence electrons, so that one odd one likes to form that 1 bond, and we're seeing it right here. Silicon, like carbon, has 4 unpaired. So what happens? They're all pairing up with silicon. Yep. Okay, what about this? Phosphorus is a nonmetal. Chlorine's a nonmetal. This is phosphorus trichloride. So what do? Phosphorus, group 5A. So I got 5. Plus chlorine, right? There's 3 of them. Each have how many? 7. Because group 7A, chlorine's in 7A. 3 times 7 is 21. Plus 5 means I have 26 valence electrons. So who am I going to pick? Who's further to the left or further down? Phosphorus. So phosphorus is the central atom, and then I have my chlorines as outer atoms on the peripheral. What do I need to do now that I determined the central atom and total valence electrons? I have to form single bonds. How many bonds did I need? 3. 2 electrons per bond, 3 times 2, subtract 6, I have 20 valence electrons. Now what do? With the remaining ones, first satisfy octets to outer atoms. That means each chlorine, which is an outer atom, would need 6 more to have an octet because they already have 1 bond. Where am I going to get the 6 more? Lone pairs. 2, 4, 6. I'm going to use 8, 10, 12, 14, 16, 18. I've used 18, but wait, 2 remain. What do I do with the remaining 2? I put them on the central atom. And what I notice is now my central atom, phosphorus, has an octet as well because it has 3 bonds. That's 3 times 2 is 6, plus 1 lone pair. That makes 8. It has an octet. And I'm done with phosphorus trichloride. So this one's a little trickier. Okay, so this is carbon disulfide. All right, so carbon has 4. Each sulfur has 2. So that's 2 times 6 is 12. Where do I get the 6 for sulfur? Group 6A. Where do I get the 4 for carbon? Group 4A. I'm always referring to my periodic table. I memorize it, but you'll be referring to it. And you're allowed to use that on every exam and quiz. So now I tally it up. I get 16 valence electrons. Okay. So who's in the center? Well, carbon's further to the right. So it's a center. And I have a sulfur and I have a sulfur. So the first thing is I want to form bonds. So 1, 2, I've used up 4 electrons. I have 12 left. So what do I do with the 12? 2, 4, 6, 8, 10, 12. So I've used that 12. I have none left. Now, if I look, the sulfur is happy, but the carbon is not. So what do? Well, I have to take valence electrons on my outer atoms that are lone pairs and actually form multiple bonds. So how do I do that? Well, I could say, look, I'm going to take this electron, those pair and move it there, and that would leave me this. Okay, so if I look, this sulfur on the right, okay, right here, it still has an octet, just like the one on the left, but carbon still does not. This is where you actually have more resonance structures, except for they're not equivalent resonance. What that means is they don't have the exact same bond distribution. They have the same connectivity. That's why they are resonance structures, but they have slightly different functions. And what do I mean? Most of you would probably say, hey, take this, right? Oops, that's too long of an arrow. And do what you did up here, add it here, and I would get this structure. And then carbon has an octet, each sulfur has an octet, I'd be done. And this is the preferred structure, resonance structure. Why? Carbon has 4 bonds. Sulfur, which is group 6A, like oxygen, likes to have 2 bonds, 2 lone pairs. You could draw a Lewis dot structure, which is valid, by instead of removing it from the other sulfur, in theory, you could draw it, and this is not correct, but I'm going to show it to you because it's still a valid Lewis dot structure, is I could have moved that there and I would have gotten this. So carbon still has 4 bonds, okay? But now one sulfur has a triple and the other sulfur has a single. So this is still a valid Lewis dot structure because everything has an octet, okay? So if I call this structure A and structure B, they're both valid Lewis dot structures. They're resonance structures. However, A is preferred. There's something called formal charge that it's a calculation to determine the preferred structure. It's like a pseudo charge that we put in these atoms, even though it's a neutral compound. This class doesn't cover that concept. So I don't want to go into something that I, don't need to for this class. What I tell students is it just looks better because this is symmetrical, right? There's 2 bonds on both sides. And you can also think of it as, remember, group 6A, like oxygen, they prefer to have 2 bonds, 2 lone pairs. That's where those bonding patterns come in, instead of a triple bond and 1 lone pair, or a single bond and 3 lone pairs. Oxygen's okay with this. It's not favorable to have 3 bonds and 1 lone pair for a group 6A element. That's why A is preferred. But again, it's still a valid Lewis dot structure because the octets are satisfied. I'm just telling you that this is the preferred structure. And you can think of, it's balanced. It's got 2 bonds on both sides. What we haven't covered is what last lecture, when we talked about polyatomic ions, and the reason why there was multiple atoms, but it still was considered an ion, was it was held together by covalent bonds. That's what the Lewis dot structure is doing for us. The lines that we're drawing are representing shared pairs of electrons, which are covalent bonds. Well, how is it that I can have an ion with such a structure? Well, that's what this is going to do. So this is not a compound. Okay, why is this not a compound? It's not neutral. So this is actually an ion. How do I know? There's a negative charge. So it's an anion. More specifically, it's a polyatomic anion. More specifically, it's an oxyanion. More specifically, it's nitrate. Why? Because nitrogen's not on that 4 that I told you guys to draw on the periodic table. So here's nitrate as an ion, okay? It needs 1 electron extra to make all of the elements in this structure happy. That's why it took an extra electron. So let's calculate total valence electrons. So the nitrogen gives me 5. Why? Group 5A. There's 3 oxygens. They're group 6A, so each gives me 6. What do I do with this extra electron? Well, I'm adding 1 valence electron. The negative charge means there's 1 more electron. So that's why I got to add 1 more valence electron. And what do I get? 5 plus 3 times 6, 18, plus 1. Whoa, sorry about that. I was getting a little crazy. Plus 1 equals 24 valence electrons. So I have a total of 24 valence electrons. I'll actually put that over here. Okay. Now I need to figure out, with the 24, who's the central atom? Nitrogen. It's furthest. Okay. So I have peripheral oxygens. First thing I want to do is I want to attach the oxygens to the nitrogen with single bonds. So each bond has 2, so times 3. I lose 6, I have 18 valence electrons. So now that I have 18 valence electrons, what am I going to do now? I am going to satisfy the octets for the oxygens in the peripheral. Each has 1 bond, 2 electrons. It needs 6 more. So what do I need to do? I need to attach 3 lone pairs, because that'll give it the octet. So that's 6 of the A remaining, 8, 10, 12, 14, 16, 18. I've used all. There's a problem. The problem is, well, the nitrogen doesn't have an octet. So what do? That goes back to what I said, that last rule. If the central atom doesn't have an octet, one of these lone pairs is actually not a lone pair. I drew it incorrectly. It's a multiple bond. So when I do that, now when I look, everything has an octet. And you're supposed to actually put this in brackets and show there's a charge on the outside. So now the nitrogen has an octet. What does that look like? Well, we can think of it as, here's the double bond to the 1 oxygen, and then the single bonded oxygens are here. Now, some of you might say, well, wait a second. Could I have removed it from here and gone there? And the answer to that is, notice here's my double bond. Yes, you could have. If I do a rotation of 120 degrees, why 120? If I take a circle and I split it into 3 pieces, a circle is 360 degrees. When I divide that by 3, this central angle is going to be 120. So if I rotate 120 degrees, like I said here, like this, I'm going to get a resonance structure where now the double bond is over here. And I've just moved everything else over 120. Now, someone might say, well, maybe I could have put the electron from over here. Well, yeah, that would have been a rotation just that way, 120. And then I would have had the double bond here. So with a 2D flat plane, we have what are called 3 resonance structures, and they're equivalent resonance structures, unlike what we had with the carbon disulfide, where one had 2 double bonds and the other had a triple and a single. These are all equivalent. There's 2 single, 1 double in each of them. But really, what the 3 resonance structures are showing, right? So here is the double bond on, I'll just call this structure A. Here's structure A, okay? Here's the double bond. All right, this is why it's nice to have a model kit. if you want to do that for yourself. They're about $20 online. But if I wrote 120 degrees, now it's at the top. It's this structure. So I just rotated 120. If I rotate another 120, now it's this structure right here. So those are 3 resonance structures for the nitrate ion. Why is there a -1 charge? I needed 1 more electron to make all of the elements happy and have an octet, but I needed 1 more. I couldn't have done it with 23. I needed 24, and that's why I needed to take 1. So I'm going to stop there for Lewis structures, because next, another reason why I keep referring to the molecular kits is we're going to be able to, from our drawings, determine the 3D shape of these molecules. It is a little tricky if you don't have kits, because you got to do it in your head, but you'll get practice and you'll see there are in my lab videos some options as well where you can go to a PhET simulation to learn how to do that as well. But I will see you guys on next lecture. I appreciate you hanging in there. And in this particular lecture, again, we took the chemical formulas, primarily dealing with all these structures we drew, had covalent bonds, whether they were a binary covalent, just a covalent with multiple atoms, or a polyatomic ion with covalent compounds. And we drew the Lewis dot structure, the 2D structure, to make everything happy and stable. And then we realized, because it's a flat plane, we can have multiple valid Lewis structures that we called resonance structures. And then next lecture, we'll take those 2D drawings and think of them in terms of 3D molecules. That's why I was talking about the rotations for those resonance structures. So thanks for watching, and I look forward to our next lecture.